Anyway, okay, we've got our speaker here, so that's brilliant. Had trouble identifying him in the waiting room, but he's here. Thanks, Mike, for agreeing tonight. So welcome along, everybody. A few new faces, a few familiar names as well come in. So welcome along, everybody. So just do my quick introduction as per usual. So just look at future meetings as usual. I've been a bit busy. So I've managed to rebook Susan Cartwright for Echoes of the Big Bang for this Thursday. So because she had internet problems, apparently she did a talk for another society and it worked okay. So it looks like her internet problems are fine. So we're getting her back this Thursday. Next Tuesday, we've got Mark Gibbons talking about fast radio bursts. And then Tuesday the 7th, we've got Martin Lewis. He's looking at his Venus night-side infrared imaging. And then on the 9th of July, it's related to this little thing. Anybody know what that is? I've hidden the date here. I took that on August 1995, just after it was discovered.
Nebula?
Down at Koa. Well, a couple of years later,
oh, right.
it produced this. And we all got excited and think, oh, it could be. And it did, surprisingly, unlike all the other comets that we keep getting at the moment. So on the 9th of July, I've actually got Alan Hale going to be talking about comets. So those who don't know, Alan Hale is the Hale in the name of the comet Hale-Bopp. So he's going to talk about comets, which is fantastic. Ian Ridpath on the 14th of July is going to talk about pictures in the sky. And then, of course, we've got Chris Lintott, Adventures in the Zooniverse on the 28th. So yeah, got a few speakers. So that's next month filled, I think.
Great, Dave.
So,
excellent work, Dave.
Oh, try my best. Anyway, from July, so really going down to Tuesday evenings, although because Alan preferred the Tuesday, I booked him for the Thursday anyway. Might do some ad hoc live streaming as they occur, and maybe a Thursday thrown in if something else good comes up. So I'm going to keep it going. Okay, and just a reminder, if you took advantage of the Affinity Photo offer, which has now gone back up to $48.99, I'm running a virtual workshop on Saturday. So if you let me know, I'll give you a discount on that. Okie dokie, so tonight's meeting, we've got Mike Poxton. I've spelt it correctly this time. And he's going to be talking about variable stars. So, Mike, if you want to share your screen, and if everybody else can turn their webcams off, that would be great, and mute yourselves. Well, if I mute everybody and unmute Mike, and then, Mike, I shall leave it with you.
Right, just need to open this. Okay, variable stars. Why do we do it? First of all, the stars are changing brightness, so that in itself is interesting. They're easy to observe. A small telescope, even a pair of binoculars, even in the case of Betelgeuse, the naked eye. One of the main reasons is they are genuinely sort of valuable scientific observations, so that's a good reason. And there's lots of them. There's several thousand, all sorts, all colours, all types. So there's kind of something for everyone to do. Now, if you can remember, quite a few years ago now, Tony Blair said he could sum up all their policies in 3 words: education, education, education. Well, I'm going to sum up variable stars also in 3 words. And those 3 words are rock and roll. Now, you might think this is a bit silly. You might think I'm sort of going after a soundbite to make it all sound incredibly cool. But I will demonstrate later that is actually literally the case. Okay? There's not much in the way of sort of variable star jargon. Just want to look at the first bit of jargon, which is a light curve. Now, really, all the light curve is, it's simply a graph of brightness against time. So as you can see here, our star is getting brighter, it's coming up to maximum there, it's fading down to minimum, and it's repeating it. Now, okay, lovely. Right, this is actually a light curve of a star called T Ursae Minoris. It's what we call a Meyer star. There are several reasons why variable stars vary. Quite a lot of them are actually pulsating stars. They're kind of towards the end of their life, and gravity and light pressure are kind of coming slightly out of balance. So the star tends to pulsate, and obviously as it pulsates, it changes in brightness. This one goes through one cycle of changes, like like this, or at least it used to, in just over 300 days. But a few years ago, it stopped doing what it was doing, and as you can see, as we come up here, up to the present day, not only have its variations got a lot smaller, but they've also got rather more irregular. But the only reason we know this is because this star has been continuously observed entirely by amateur astronomers. So, the sort of like to us lot, we can all do something, because this actually shows stellar evolution actually in practice. It's actually happening before our eyes, if you like. And you just need an average sized telescope to now see this star at minimum. Because whereas its minimum magnitude down here used to be like sort of 15, now it's about sort of 12.5. So a small telescope will actually show it. And obviously, because something is happening to it at the moment, it's a star that needs constant watching. So if we just go on to the next slide. This is another light curve of a star that I'm actually studying myself. This is a completely different shape, as you can probably see. Really what we've got here is a very young star. And it's going through all sorts of interesting procedures at the moment. It's actually in the process of forming planets. And really what's happening is there's a swirling sort of cloud of gas around the star, and some of that gas is now actually coalescing into planets. And as that clump, they call them clumps, it's just a sort of a protoplanet, if you like, it comes between us and the star, and it makes the star get fainter. This is a particularly interesting star. I've actually written a paper on it. We will come back to young stars a bit later. That's my nice sign-in name is Baby Star Man. I sort of study baby stars. Okay, now what we've got here is a star that you might have heard of. It's called Laugol in Perseus. It's entirely visible with the naked eye. And really what happens here is we have two stars that are very close together, and they happen to be in our line of sight. So occasionally one star will pass in front of the other and make its light sort of diminish. Okay, right, so here we've got something old and shrunken, and also a potato, and here we've got an avocado. Now here the potato represents the brighter star, and the avocado represents the fainter star. So as the brighter star passes in front of the fainter one, the system will get slightly fainter. But as the stars go around each other, and the dark one passes in front of the light one, that's when we get the dip in brightness, as you can see on the little light curve there. So that's a constant kind of change in brightness. It's repeated time after time after time. As you can see, the actual sort of period between the two big minima is about sort of 2 and a bit days. There are lots and lots of this type of star in the sky. Obviously, they're not all. They don't all consist of a small bright star, and a big faint one. There's all sorts of possibilities. For instance, you can have two stars that are equally bright, and in that case, you get constantly changing light curve. One star that probably a lot of people are familiar with is Beta Lyrae. That's exactly that sort of star. It's made out of two bright stars that keep eclipsing each other. These are sort of what I call fake variables. They don't actually vary. They just appear to vary because of where we are, because the stars revolve around each other in our line of sight. So we're kind of looking at sort of equator on, if you like. So that's basically how an eclipsing binary works. But like I say, they're not real variable stars. Okay, now we talked earlier about pulsating stars. These probably form about sort of 75% of the whole class of variable star. There are lots of different types. The one at the top is a Cepheid, like Delta Cephei. They are pulsating stars. As the stars get bigger and possibly older, they get a bit less kind of regular, because Cepheid variables are very, very regular. They change in a sort of clockwork fashion. You can kind of set your watch by them if you like. But as the periods get longer and as the stars get bigger and cooler and redder, as you can see here, they start doing all sorts of weird things. They are not nearly as regular as the Cepheid variables. These are stars that we call long period variables, or even Mira stars, after Mira here. Of course, that was the first one to be discovered. That's why they call it Mira. That's just Latin for wonderful. So, they thought, oh, here's a wonderful star. Sometimes we can see it and sometimes we can't. They do tend to have certain things in common. As you can see with the Cepheids here, the rise to maximum is quicker than the fall to minimum. But sometimes we get stars like X Camelopardalis here, which are all nice and sort of symmetrical. They don't do that, and then you get TCAM, which is actually not far away from this star, where you've kind of got a little, well, I really hesitate to call it that. That's sort of a nipple on the top. That's probably just my filthy mind. So there's a whole kind of zoo here of variation, lots and lots of different stars. Now we come to another kind of variable that lots of amateurs like to follow because they're so sort of exciting and unpredictable. These we call dwarf novae. In fact, there's not a lot of difference between the dwarf nova and an actual nova. Basically, they're both composed of two stars, one of which is a white dwarf, one of which is slightly bigger than a white dwarf. It's not sort of huge, it's not Betelgeuse size, but probably a little bit bigger than the Sun may be. But the white dwarf, being the more massive star, tends to pull material off its kind of big brother, if you like. And this material builds up in an accretion disk, what we call an accretion disk, around the white dwarf. And for various astrophysical reasons that I don't really want to go into here, this is the seat of the explosions. If we could take a star like SS Cygni, which is probably the best one to follow if you're just kind of getting into this sort of thing, its normal minimum magnitude is about magnitude 12. But every now and again, roughly about every month, I suppose, it will erupt straight up to magnitude 8 very, very quickly. Sometimes in the course of a day, sometimes even quicker. And then having done that, it falls back to minimum. You wait a few days or a couple of weeks, 3 weeks, off it goes again. It does the same thing. But as you can see here, it doesn't repeat itself from one to the other. And here, for instance, you've got all sorts of fun and games going on. And in fact, just a few weeks ago, it started entering a similar phase. It started brightening and it stayed bright for ages and ages, and then it started to fall and then it brightened again. So it's always doing something interesting. And the really nice thing about SS Cygni is it's in the same field as a beautiful golden star called 75 Cygni. So it's just worth looking at for that. We have a subgroup which we call the Z Camelopardalis stars. Camelopardalis is a brilliant constellation for variable stars. Here, you think it's going to do the same sort of thing as SS Cygni, be coming down and up and down, but then it will kind of take a sort of a furlough, if you want to use the current term, and it will stop varying altogether. And in fact, at the moment, we are in one of these so-called standstills, and there's absolutely no predictability as to when it's going to enter a standstill or when it's going to leave one. So again, the very irregularity means they need constant changing, because what we find out from all these various studies is, kind of what's going on the surface of the stars, and it all adds to knowledge. Now, this is my big thing. I study sort of baby stars, if you like, hence the name. These really are stars that either are forming or have just formed out of the gas clouds that all stars are made out of. Their changes in light are usually very, very rapid. Although sometimes, you know, you get what are called the T Tauri stars, and I really, really want you to remember that name. All right, it's not remember the name Wayne Rooney; it's remember the name T Tauri, because we will meet it near the end. Okay. In the case of the T Tauri stars, which are very, very young stars, their changes aren't quite as sort of suicidal as some of the others. They look a bit like sort of Cepheids, except they're not very regular, because as you can see, this one kind of looks okay, and then it decides to do something completely unpredictable. And again, this is a really good reason to observe them. In fact, these two stars, AB Aurigui, which is entirely visible in binoculars, by the way, you don't even need a telescope. AB Aurigui and SU Aurigui are actually the two members of a double star. They are sort of connected with each other, so in fact you can observe them both at the same time. Many billions of years ago, the Sun was a T Tauri star, because the thing that distinguishes these objects is they are about as massive as the Sun, between about a fifth as massive and a couple of times as massive, probably at the very top limit. But they are essentially stars like the Sun. But they are baby stars like the Sun, and they are throwing tantrums in the stellar nursery. They haven't quite learned the rules yet about how you behave. So again, very, very, very interesting to watch. Now, as we move up the sort of mass scale, and we get slightly hotter, more massive stars, the changes get very, very weird. Here we have RR Tauri. You will see a lot of Tauris here, because quite a lot of the constellation of Taurus is one big star-forming region, so there are lots of very young stars there. This is a star that can change over the course of a night, basically. In fact, there's another star very close to it called CQ Tauri that I've actually seen fading in front of my eyes as I actually look at it. So, you know, it's not a question of these takes several days or weeks to change, like the long period variables do. These ones do it all over the place. If I can come to the last one, as you can see here, this is very, very active and a very, very strange star indeed. To begin with, it's such a recent discovery that it didn't have a proper variable star name to start with. It's just called MISV1147. It's a bit of a mouthful, I know, but V730 CPI is a lot easier. Its normal magnitude is about magnitude 12.5. Well, except it doesn't really have a normal magnitude, as you can see, because it changes all the time. It can fade right down to magnitude 16. And I know that because this data point here is actually mine. It's the faintest the star has ever been seen. That's about magnitude 15.7, I think. But later the same day, it climbed right up here. So very, very fast variation in in a short amount of time. It's a nice little star to observe. It's quite close to an 8th magnitude star, so you need a fairly high power to see it. But if you watch it over the course of, well, even a week, you can see it actually doing something. And this week, we think this is an extremely young star. It's barely a star, in fact. Right, I just want to show you some pretty pictures now, because lots of these stars are involved in nebulae. So there we are. I'm sure lots of people, certainly Sean will recognise that. That's the Elephant Trunk Nebula. IC 1396, which is in Cepheus, a really good constellation to look at. Lots and lots of variable stars here. You can't necessarily see them, but inside this bit of the actual trunk here, the bit that looks dark, it only looks dark because we've got a dark nebula going on there, and it's obscuring the light of stars on the other side of it. A bit like the Horsehead, for instance, or the coal sack. If you look at this area with, say, something like X-rays, we actually find there's about 300 forming stars just inside this small area. And there's a particularly interesting variable star close by, which is this one here. That is called GMCPI, and that's a star much like the last one we look at. It changes in brightness all the time, between magnitude about 13 and 16. Okay, that's quite a faint one. But as we saw earlier with AB Origi, some of them you can see with binoculars. This again is something that a lot of people might recognise. This is Hubble's Variable Nebula in Monoceros. We're not sure if the nebula varies because the star at the pit, which is called R Monocerotis, varies itself, and thus seems to make the nebula vary. We're really not sure. It's probably more a case of the interplay between the two. So, right, what I really want to draw your attention to here is the green bit coming out of what looks like a sort of an interstellar hamburger, if you like. Where the meat would be in the hamburger, it's dark, and the reason it's dark is that's where all the gas and dust that are forming the star is actually located, and it's not hot enough to actually sort of shine. Now, at this moment, we need to do another little demonstration. Can you see me holding a small glass?
Yes, just about. You hold it up a little bit higher.
Okay, right, one small glass. How's that?
No, you're too high now.
How's that?
No, up a little bit, up a little bit. You should be able to see your picture so you can judge.
Actually, at the moment, right, I don't need to share, do I? Oh, there we go. Okay, right. So our small glass here, it sort of represents the forming star. Now, at the moment, there's nothing in it, so we need the object that should be in every single astrophysics laboratory in the world, which is a bottle of cassis. Now, the cassis is going to represent the actual sort of gas. So, okay, here comes the gas. The gas is forming onto the star. It's filling the star up. The star's getting bigger. Hope you can see that. The star's getting bigger and bigger and bigger. There's more cassis in there. The star's getting bigger. As it gets bigger, it gets more massive. It gets more gravity, so it sucks more stuff in. It sucks it in, sucks it in, sucks it in. Oh dear! Oh no! Right. The cassis has unfortunately overflowed the star, so I have to drink a little of it. Ah, there we are. Okay. Now, really, what's happening here? If I can just go back here. Okay. So we are now sharing again. Sorry, I've got cassis all over my fingers. Right. The fact that the cassis overflowed the little glass means that all the gas was falling onto the star. But there comes a point where the star can't take any more gas on. So what happens to that gas? The fact is that it's expelled through the poles of the star in what we call a bipolar airflow, which makes sense. So there are two poles, and it's flowing out. That gas can then go on to start off star formation somewhere else in the neighbourhood. So it's kind of a fractal process, if you like. You know, you start off with one, and that causes others to do exactly the same thing. This is a particularly good example because you can see everything in action. Here's the equator of the star, and here are the poles, and here's the stuff actually coming out. The reason why this happens is because normally all the gas and dust would be falling onto the star. So why don't we have stars that are absolutely huge? Because all the gas and dust in this big dust cloud is falling onto the star. Well, what actually happens in this case is there comes a point when the star gets so massive, and obviously more mass means more pressure at the middle of the star, and the more pressure you've got at the centre of the star, the hotter and hotter it gets, and it eventually gets so hot that it starts nuclear fusion, and that tends to blow stuff away rather than suck it in. So now we're at a point where hopefully the two forces of of the sort of nuclear force in the star and the gravity are starting to come somewhat into balance. That's the reason why a lot of these very young stars actually go through these variations, because that process is still going on. And here you see some more bipolar airflows here. Obviously, the way they look is sort of largely dependent on really where we are when we look at them. Here we're looking at equator on. Here we're not. We only appear to have one here, and it's in a kind of funnel shape. Now there will be another funnel. It's just it's on the far side of the star, so we can't really see it. So all sorts of fun and games. Here's another pretty picture that a lot of people might be familiar with. This is the Propeller Nebula, whose designation escapes me for the moment. I know it's in Cygnus, which again it's a big star-forming area. So here we have our nebula, and here I think, because this is still largely theoretical, we have our bipolar outflow. But our bipolar outflow in this case isn't straight, like the first one we saw, with the green coming out the top and bottom. And it's not a fan shape like some of the others. We think what's happening here, again, this is the dark bit, this is the star has, where the gas isn't quite hot enough to shine yet. And we think these are the bipolar outflows, because what may be happening is there's another star hidden behind the one that's causing this. Although we can't see it, it's having a gravitational effect, and it's kind of bending the bipolar outflow into this S shape. So again, all sorts of fun and games going on. I don't really want you to read this. The whole point of showing this is there are a lot of question marks, and possibly this, possibly that. And the whole point of showing this is to show how much we don't know, which again is another good reason to study these sort of forming stars. Okay, so we've had a little look at the sort of variable star zoo, and really what I want to do is to give you some idea of how to do it. So the first thing you need to do is to recognise what various magnitudes actually look like, and really more importantly, to recognise what the difference between magnitudes look like. So if it's clear tonight, go out and have a look at the Northern Cross of Cygnus. All these stars in the cross of the cross, if you like, they're all roughly sort of second magnitude, but the difference between gamma here and epsilon here is 0.3 of a magnitude. So if you can see there's a difference between these, that's a really good start, because that's what you need to do in order to observe a variable star. I'm talking purely visually here. I'm only observe visually. So this is my point of view. You need to sort of hone this skill until you can see differences of 0.1 magnitude. That's kind of the ideal to aim for. All right, you don't do that right at the start. It kind of comes with experience and practice. So if we just look at Albirio down the bottom, everyone knows Albirio, don't they? Lovely coloured double star. So the difference in magnitude between Albirio here and Delta Sigma here, that doesn't have a name, poor thing, is 0.2 of a magnitude. So if you can see the difference between those two, you're well on your way to becoming an expert variable star observer. But most of the stars that we observe, you need a proper star chart for. So this is what an AAVSO star chart looks like. Here's the star I was talking about earlier, 75 Cygni. That's a beautiful gold colour, so it's worth looking at, kind of just for that, really. Now, the star we're interested in is SS Cygni, and it just so happens to be inside a nice little triangle of fairly bright stars here. Now, these numbers just tell you how bright the stars are. So 86 means it's magnitude 8.6. We don't put the decimal point in case anyone confuses it with a faint star. So yeah, so this is 8.6, that's 9.8, that's 10.9, 12.3, and so on. And basically the technique is to sort of place the variable star between one star that's a bit brighter than it appears and another star that's a bit fainter. So two good ones to pick here would probably be 86 and 96. So if you think it's halfway in magnitude between the two, then obviously the magnitude is going to be 9.1, because the difference between those two is a whole magnitude, 1.0 magnitudes. So if this is exactly halfway between them, the difference is going to be 0.5. So you subtract that from 8.6, which makes 9.1, and it also, also occurs with that as well. You do the same thing, except it's 0.5 magnitude brighter. That's basically how it works, and that's kind of what we do. When you're starting out, in fact, even not necessarily when you're starting out, it makes a lot of sense to actually do it sort of graphically, to sort of place it on a line. You can record your observation like that. I wouldn't recommend actually sort of sending it off to a proper body like the BAA like that. But when you first start out, sort of practicing, it makes a lot of sense to do it graphically, because you can kind of see it before your eyes. Right, now, I just want you to come back to what I said earlier. I said, remember the name T Tauri, didn't I? And I also said that variable stars are rock and roll. Well, I'm not kidding. Of course, this is a Dutch band. It's a Dutch rock band, and they are called T Tauri. So variable stars really are rock and roll, you see. So I thought I'd just get that one in. I'd just like to show you some of my holiday snaps. In 2002, as an active observer with the AAVSO, I got invited to an astrophysics conference on the Big Island of Hawaii. And as part of it's about a couple of weeks, as part of that time, we had a little excursion up to the top of Mauna Kea, and there's me beside the keg. So, study variable stars and see the world. Okay, so then fire questions if you want.
Okay, thanks very much, Mike. Okay, so if anybody has got any questions for Mike, you should be able to unmute yourself. Let me just check. Yep, you can. So if you've got a question, please ask Mike. Did you mention what the AAVSO was, Mike?
Oh, right, yeah.
I know you mentioned it, but you may not have actually said what it was.
There are various organisations in the world that study variable stars. For instance, in Britain, we've got the BAA Variable Star Section. The AAVSO it's allied to Harvard University in the States. It stands for the American Association of Variable Star Observers. But strangely enough, it has observers all over the world, literally all over the world, south of the equator, north of the equator. Several. I'm sure Gary is listening. Gary Poyner over here is a member of the AAVSO. Obviously, I am too. There are people in Hungary, Finland, South Africa, Australia, New Zealand, South America. But basically, the AAVSO is now the repository of all the variable star observations in the world. So it's a useful kind of clearinghouse, if you like, for the observations that people make. And as I say, really, in order to do it, you don't even need a telescope. A pair of binoculars is quite sufficient. Obviously, the bigger the telescope you have, the more stars you can see. So that's a good thing.
Where do you get the star charts from?
You can download them off the AAVSO website.
Oh, right. Okay.
Absolutely free. And you can customize the charts. For instance, if you've got a non-inverting telescope, you can have the charts done so that north is at the top. If you've got a sort of telescope that reverses it laterally, you can do that. You can set the limiting magnitude that you want to show. You can ask to plot other variable stars that are nearby. You basically play about with it.
Right. So that's from the what? Sorry, was he from the? What did you say it was from? The.
It's the website is just aavso.org.
ABS.
I'll stick it in the.
Yeah.
Thanks.
Put it in the chat. aavso.org.
Yeah.
Gerard's put a question on Mike. Heard you can make observations of variable stars using the DSLR and doing reduction to the results. Can you outline what was required, and does a reduction differ for different DSLRs?
I know nothing of DSLRs. I'm not even sure what it stands for. So on that one, I'm probably going to say I don't know. That's the honest answer.
I just wanted to clarify your star diagrams you had when they were talking about the magnitude. Was the magnitude depicted by the diameter of the little circle?
Generally, the conventional way to show a variable star is an open circle. That's just kind of convention. Generally, on star charts that you'll get from the BAA or the AAVSO, the size of the disk is some sort of guide to how bright the star is.
Yeah, that's what I meant. Thank you.
Ah, lovely.
Gary just put you need a V filter, apparently.
All right. Yeah, that's not quite the same as visual. It's kind of near enough.
Right. Any other questions from anybody?
Sean trying to think of something different.
I know. I remember a question that we talked about was about observing variable stars and binaries and what have you. And yeah. But I think you've sort of observed them anyway. Some of those, haven't you? Obviously.
Yes. Yeah.
So I'll leave it there then.
And of course, Nick Curie a couple of weeks ago showed the globular cluster. I can't remember which one it was now, with all those variable stars within it too. So there's plenty out there.
I mean, there is a whole sort of group of stars which are called cluster variables because they are found extensively in globular clusters. They tend to be stars that amateurs don't observe because they're very regular and predictable, and amateur astronomers tend to observe the unpredictable ones, because they're more fun, really. Because you don't know what they're going to do next.
Any other questions for Mike? No? Okay, right. Well, thanks so much, Mike, for telling us all about variable stars. I hope a bit more of an understanding of the different types, etc. Hello. Yeah, it's always a little bit like drawing graphs for me. And it's a bit like when I used to have a proper job. I used to have to draw graphs all the time. So it's not something I really enjoy doing when I'm doing my hobby. So yeah.
You don't have to draw the graphs.
You don't have to draw the graphs.
In fact, the AAVSO website has also got a light curve generator where it will draw the graphs for you.
Oh right, okay.
Which is fun. Yeah, you can then sort of print them out or just look at them, and you can plot all sorts of observations. You can sort of plot the various filters on there.
So it looks like it'd be worth going into the AAVSO website and having a look and seeing what resources there are. Yeah,
it's a very extensive website.
Excellent. Okay, I know I've delved in there a few times to pick up a chart now and again, but I've not really explored it extensively. So
please explore.
Right.
go boldly where few have gone before.
Okay. Okay. No more questions? No? Well, thanks so much, Mike, for telling us all about variable stars. You're keen to get off to watch the footy match next, aren't you?
I am. My team are playing tonight, the mighty Spurs.
Good stuff. So thanks for giving the time to tell us all about variable stars. Thanks everybody for joining in, making it the success it is. And so keep safe, keep well, and keep looking up.